Dear students, welcome to the online class. I am Dr. SSC Hiremat. In this video, you are going to study about the thermodynamics of electric double layer. Electric double layer, it is also called as the electrified interface. In this video, we are going to derive the Lippmann's equation. That is nothing but the thermodynamics of electric double layer. Now about electric double layer. When a metal is in the contact with its solution, then it gives electrons. Thus, there is equilibrium between the metal and ions. Thus, the metal gets negative charge and the solution gets positive charge. It can be represented in this way. Suppose this is a metal rod. Dipped into a solution. Thus, the metal surface gets negative charge. This is one electron, negative charge. Now you think about the ions present in this solution here. As the surface is negatively charged, the solution contains positively charged ions or cations. Then each cation is surrounded by water molecules. That is the required number of water molecules. Then, as it is negatively charged, the positively charged ions try to come nearer to this surface. Then what happens? Suppose this is one cation. It is surrounded by water molecules. Suppose water molecules are represented by the empty spheres. Okay. And another water molecule. Suppose here it is another ion. Okay. In this way, each ion, that is oppositely charged ion, is surrounded by water molecule. By doing so, the surface of the metal, there one layer of the water is formed. And here another layer of the positively charged ions is formed. Thus, this is one layer and this is another layer. One layer means the metal surface, and another layer, there is a layer of the oppositely charged ions. In between there is the interface. And as it is negatively charged and it is positively charged, there is the potential difference. This is called the electric double layer, and it is also called the electrified interface. This is one phase and this is another phase, and in between them there is the interface. Thus, the electric double layer interface is represented in this way. This is one delta, and this is metal, and this is solution. The electric double layer or electrified interface. M is equal to metal, S the solution, and delta the interface. Now, let us study about the thermodynamics of electric double layer formation or the electrified interface formation. That is nothing but the derivation of the Lippmann's equation. Now, from first and second law of thermodynamics, energy change in a closed system is du equal to TdS minus PdV. Suppose this is equation 1, where U is the internal energy. For a open system, energy energy change is, that is summation of mu I d n I. Suppose this is equation 2. Here n is the number of moles of ith component with chemical potential mu I where expel. Then equation 1 becomes du is equal to T ds minus P dV minus summation of, that is I, mu I dni. So this is equation 3. Now, by the formation of electric double layer, the change in the surface area during the formation of electric double layer, the surface area changes by dA and surface tension or interfacial tension, it is interfacial tension is R. Then the change in energy is equal to mu into dA. Suppose this is equation, that is 4, and this is 5. Then the energy change due to the formation of electric double layer is equal to m metal surface, delta interface, S, and pi is the potential difference, and dq is the change in energy, where already we have defined the m delta S. P is potential difference, and dqm is equal to change in charge. Then the total energy change total energy change from equation 3, 4 and 5 is equal to that is du equal to as it is, that is T ds minus P dv 1 minus summation of mu I dni, okay, for all ith component, then minus nu into dA, this is from equation 4, minus m del s phi and dqm, okay, this is equation 6. Means the equation 6 shows the total energy change, one by the entropy change, another by volume change, another by expelling the chemical, that is the nth component, and by the surface change or surface energy change and the potential developed. By all these processes, the energy change is given by equation 6. Now about intensive properties and extensive property. Here this is the one is intensive property and another is extensive property. That is energy change equal to extensive property into intensive property. Extensive property into change in intensive property. Change in intensive property. Thus, what are the intensive properties here? Here, the intensive properties are that is T, P, mu, nu and delta pi. These are the intensive properties. Then extensive properties. Remaining are the extensive properties. That is S, phi, n or ni, a and qm. These are the extensive property. Okay, extensive property. Thus, the total energy change is calculated by multiplying the extensive property by intensive property. The extensive properties are these and intensive properties are this. Now, if we take the absolute values, of the properties by taking absolute values of the above properties, the equation 6 becomes absolute value for du, that is u, then T s minus P phi minus summation of m I n I minus nu A minus, that is delta ms pi and qm becomes this equation, that is equation 7. Okay. On differentiation of equation 7, on differentiation of equation 7, we get du equal to, that is total differentiation, you are going to get this equation 1. Okay, that is t ds minus p dv minus summation of mu I b ni minus nu dA minus m delta s p d qm. Now all the extensive properties were differentiated. Now keep the extensive property constant and you differentiate with intensive property. Then you are going to get, that is s is kept constant and dt is differentiated here. Okay. Then p is kept constant minus v is kept constant and tp is here minus summation of n is kept constant ni and mu I is differentiated. Then minus a is kept constant, nu is differentiated minus here qm is kept constant and this is, that is differentiation of, that is m del s p. Suppose this is equation 8. From equation 8 minus equation 6, we get this is the total, it is from equation 6 and this is from equation 7. Therefore, if we subtract equation 6 from equation 8, left hand side is only du, then this becomes 0. This becomes equal to 0, left hand side. Then this is equal to s dt minus v dp minus summation of ni d mu I minus a d nu, then minus q m del s, that is differentiation. This is equal to differentiation of this, that is differentiation of m del s phi. This is suppose equation 9. Here, by subtracting equation 6 from equation 8, left hand side being the du only, this becomes 0 and other becomes as it is. Now, at constant temperature and pressure, equation 9 becomes, this is equation 9, becomes this term is equal to 0, okay, and temperature is constant, this term is 0, and pressure is constant, this term is 0, then you are going to get, that is minus summation of ni d mu I minus a d gamma, that is surface tension, minus q m d m del s phi, and we may take this as the plus, and all are changed, minus minus minus, this becomes plus, and this is equal to 0. We may write this is equal to 0. Suppose this is equation 10. Okay, then the equation 10 is at a constant temperature and pressure. The effect of temperature and pressure is 0, and remaining terms are here. Dividing equation 10, dividing equation 10 by A and rearranging we get this. Let us take this on the left hand side, and suppose this is A d nu, and you take all others on the right hand side, that becomes minus mu summation ni d mu I minus qm d m del s pi. Okay, then this is rearrangement. Dividing the both side by A, you are going to get this A divided by A. Suppose this is equation 11. Equation 11. Dividing the equation 10 by A and rearranging, we get d gamma equal to summation of this and this. Equation 11 shows that equation 11 shows the change in surface tension depends upon change in chemical potential and change in potential across potential at interface, but both depend on change in composition, that is change in number of moles. Change in number of moles. It can be explained by using a term surface excess. Suppose Ni is the number of moles at a surface. Ni naught is the number of moles at bulk, and capital gamma I is called surface excess. Then Ni divided by A, that is number of moles at a surface per unit area. is equal to surface axis plus Ni naught divided by A, where to that is capital gamma I is the surface axis of the ion I. Suppose this is equation 12. Equation 12. By multiplying both sides, by mu I, that is d mu I, change in chemical potential of ith component then equation 12 becomes Ni mu d mu I divided by A. This is equal to capital gamma I into d mu I plus Ni naught divided by A d mu I. For all the components, we may write summation of Ni d mu I divided by A is equal to summation of gamma I d mu I plus summation of Ni naught divided by d mu I. From Gibbs-Duham's equation, we know summation of Ni naught d mu I is equal to 0. Summation of Ni naught d mu equal to 0. Then equation 13 becomes summation of Ni d mu I divided by A is equal to summation of capital gamma I d mu I. Here, when this and this becomes 0, divided by A, that becomes 0. Thus, summation of Ni naught d mu becomes 0, then this term disappears. Suppose this is equation 14. Now, to calculate the total potential difference, let us go to the diagram once again. Suppose this is one electrode, suppose this is metal 1, and there is another metal, suppose this is M2, then these are negatively charged and there is interface between them. Okay, thus we may write this is solution and this is delta, and here this is solution and delta for two metals, and these two are connected, we may represent it as M1 del m2 m2 m2. Then the total potential difference may be represented as phi. Then the total potential difference may be represented as this. Thus the total potential difference, the total potential difference is equal to, suppose this is V, which is equal to, by this process at this electrode and another process at this electrode, and due to the metal-metal interface. This is equal to m1 del s, then pi plus, if you start in this direction, that is s del m2 pi, and as you are moving in this direction, this is also, that is m2 del m1 pi, m1 pi. Okay, this phi potential difference, phi equal to this is phi. Okay, on a differentiation this equation, we get d phi equal to d m1 del s phi plus differentiation of s del m2 phi plus differentiation of m2 del m1 phi. Here m1 m2 are the pure metals, and differentiation of this you are going to get, this is equal to 0. This is equal to 0. Then this becomes dV equal to, that is dV equal to d m1 del s phi plus d s del m2 phi, or plus dsm2 minus dsm2, sm2 15. In equation 11, the interfacial area A may be taken as unity, that is A may be approximately taken as unity. Then the equation 11 becomes d gamma is equal to minus qm into d m del s phi minus summation of n I divided by a into d mu I. It means equation 11 is rewritten in this way. From equation 11, 14 and 15 we get this is 11 rewritten, that is d nu equal to, now minus d m1 s pi minus d m1 s pi is equal to this, you may write, that is minus qm into d phi minus qm divided by a, as it is qm divided by a differentiation of s del m2 phi, then minus from equation 14, this term is equal to, that is summation of capital gamma I divided by a into d mu I. So this is equation 16. Now from equation L1, 14 and 15 we get suppose this is L1, that is d gamma is equal to minus qm, this term is equal to this term, then let us write this qm divided by a, that is equal to this is equal to, that is dv sign as it is, then plus this is equal to q m divided by into d s del m2 pi plus minus summation of capital gamma I into d mu I. So this is equation 16. And a non-polarizable second electrode is used, and the second electrode that is metal, second metal is non-polarizable, then d, that is s del m2 p becomes 0, that is change in potential becomes 0, that means suppose this electrode is non-polarizable or non-attackable, okay, non-polarizable or non-attackable, okay, and another condition, at constant composition, or concentration, that is d mu I is also equal to 0. Means when a non-polarizable electrode is used, this metal is used, this term becomes 0. At a constant composition, when the composition is kept constant, this term also becomes 0. Then equation 16 becomes, at a constant composition, the equation 17 becomes, that is divide this by this, that is at a constant composition means that is partial differentiation d mu divided by dou v at constant composition is equal to minus qm. This is equation 18. It is known as is known as Lippmann equation. Lippmann equation. Now, the above Lippmann equation can be rearranged in this form: dou gamma is equal to minus qm into dou v, or gamma is equal to minus qm into v. Here the potential V is variable with gamma, that is surface tension, or surface tension is variable with potential V. Now, by plotting a graph of surface tension that is gamma versus potential V, we get a diagram which is known as electrocapillary curve. It is known as electrocapillary curve. It is as follows. Here we are going to draw a diagram, that is graph gamma versus V. Gamma is nothing but the surface tension, V that is potential V. We are going to get a diagram of this nature. Now, to get the charge density at any point V, we draw a tangent to the curve at that point. Then slope of this curve, that is tan theta, gives minus qm. Now, slope of the curve at any point V gives the charge density qm.